All right, why don't we get started? Hopefully we won't have any more 20-minute Windows update delays. So we're going to start off by finishing up the slides that we had from the last time. So the first thing you want to... Uh-oh. It's just a joke. Anyway, so we had talked about what sockets are. So sockets to the kernel are just the endpoints to communication, but to an application, it's a file descriptor like a client FD, server FD, in which if you read or write from that, you effectively get to the other side of the network. And the main distinction between these and other file descriptors that you're used to is the way they're set up. And that's what we'll talk about today. But first, we need to talk a little bit about what the address structure looks like for a socket. So the idea is to be very generic. And so the generic version of it is just there's this socket address family that you fill in, and basically all the other bytes are family specific. Okay, so the generic one just has the two fields, protocol family and the address data. Okay, we'll use this casting convention that we'll type def this struct to the letters SA, to name it SA. Okay, so that's the generic, but what does the specific one look like? So for IPv4, which again is what we're going to focus on in this class, if you put AF INET in the family field, then that specifies as IPv4, and so that also specifies what the other fields mean. So there's a port field, which is the port number in this network byte order. There's IP address in network byte order, and then since this protocol, that's all the bytes we needed, it's just padding after that. Okay, so to get from the generic to the specific, then you have to do casting from one to the other. So there's these routines, one that goes each direction. The first we'll talk about is get address info, and that goes from the string name to the socket address structure, to one of these structures. Okay, and the advantage of get address info over what it replaced, get host by name and get served by name, is that it's protocol independent. It's the main advantage. Okay, so if you use get address info, then no matter what the protocol is, it'll do the right thing. It's also re-entrant, so it can be safely used by threaded programs. The disadvantage is that it's somewhat more complex, but fortunately there's only a small number of patterns that we tend to use. So this is what this looks like. You have the host and the port of the service name, and you get back a result, okay, based on that. There's also these hints, which can help guide the search for things you're looking for. We'll not really get into those today, but if you look at some of the slides that are in this deck, they'll talk some more about the hints. Then if we have a structure, we also have a way of freeing that information, and also a convenient way to print out an error message based on an error code. Okay. So what really happens? So when you call get address info, you actually get back a pointer to a linked list that looks something like this. Okay. So in the linked list, there were one or more of these address info structures, okay, that we just saw on this previous page, right? And the important thing is that it allows you to have more than one that could potentially match the what you're looking for, right? So you come in, you give it a host and a service, and it could give you choices, different socket addresses. So in this particular picture, you've got three choices that are all just linked using these next pointers, and they point to these structures that I showed you before, the ones that have the actual byte ordered address, IP address, and port number. So what happens? You get back a client, for instance, will get back one of these lists, and we'll walk through the list and we'll try each one in turn. Okay, so we might try the first one and say, oh, can I, can I successfully create a socket and successfully connect based on that one? And if not, I go to the second one. If not, I go to the third one. And only if it fails on all of them, then I return an error code. Okay. Similarly, a server will do the same thing. After it calls get address info, it'll get one of these linked lists, and it can go one at a time until it finds one that succeeds in sort of establishing the preparing for the connection. Okay, so important thing to remember here is this linked list. We will get into these different socket connect, socket bind over the next few slides. So in fuller detail, address info structure contains not just sort of a pointer to these structures and the link of the list. It also contains some arguments that you can pass to the socket function. Okay, and a canonical host name. So if there's some sort of canonical version of the host name, you can get that from there as well. Okay. So the converse of that is get name info. The inverse, it converts a socket address to a corresponding hosted service. And again, it's protocol independent. So what it does is you take in a socket address, okay, which is here, just one of those pointers, one of the structures, and the length of it. And what you get back is you get back strings that indicate the host and the service. Okay, and then there's also some optional flags, which we won't get into. And so that's sort of the highlights of the stuff that we needed to wrap up from the last time. Any questions on that? Okay, you'll see it flows nicely into what we're about to talk about today, which is this deck. Okay, so welcome to Thursday's lecture. All right, so the review, remember we had a picture like this on Tuesday where you started with a server who would get started up and perform all these tasks. Then you could start up a client, okay? It would generate a connection request. And then once this connection was established, you have a series of data being exchanged. In this particular case, we were doing the simple echo server, right? So all you're doing is you're reading from the terminal, you're writing to the socket, it shoots it over here, it gets read from the socket on that end, and it's just echo, it just immediately copies it to the socket the other direction, and it's read and then echoed at the terminal. Okay. After you've done that for a while, there's a close, maybe you control the seed out of it or something, and what that ends up getting a end of file. The next time there's the socket read, and that tells the server to go ahead and drop the client. Okay, and go back to here and await requests from a client. All right, and as I mentioned last time, this shows an example where there's just one client at a time, but of course these servers can take hundreds of thousands and tens of thousands of clients at a time. Okay. And then just again to review in terms of I/O and C, they have standard I/O functions they're familiar with here. Unix systems calls for things like opening and closing files. But what we want you to use in this course are the Rio versions, the wrapped versions that handle on your behalf, various kinds of error checking signals and what we call short counts. And so there are these functions here that you use. And so when we depict a picture, then this becomes a f gets, and then you do a Rio write n, since you know the length of it. This reads in a buffer and then writes it back out and so forth. Okay, so that's what it ends up looking like when you use the Rio library and the actual Unix systems calls. Any questions so far? Okay. All right. So now we're opening these boxes. Okay, we're going to start opening this box and this box. Okay, and see what actually gets done. All right, and so you can see the steps that get done here. We're going to proceed as highlighted in lavender. Okay, so the first step for each of the server and client, again, there's no particular ordering from them at this point, is this call to get address info. Okay, and again, it gets you, generically, it gets you back just this, some family code and some family specific data. So if we want IPv4, we have to actually specify that. And then we can get something back looks like this. Okay, and from that, we can get the port and the address. Okay, and so the end result of that is that we have, this structure that's this pointer to the structure that has the address, the information we need. Okay. Then, and again, this. Okay. So then each side can call a socket. What does the socket call do? So here. So this is showing an example on the client side. So client calls socket. It says, I'm interested only in sockets that are, doing IPv4, that we want to communicate using IPv4, and that, this is indicating that it's going to be the endpoint of one of these connections. Okay, so based on these two flags, that's the domain, the type, and the protocol. We're just using the default of 0. We're able to get a file descriptor that's going to correspond to appropriate socket. So it's going to walk through the linked list, find the socket that matches and is good to go, and create this file descriptor on the client side. The server will do the same thing and get one for the server side. And so that puts us here. So let's call the one on the server side listen FD, because eventually it's going to be listening on that file descriptor. And here's the client file descriptor FD. So that's kind of it for what the client can do at this point. The server's got the next step, which is bind. So bind, you give it a socket file descriptor, and you give it a one of these pointers to a socket address thing, specific one, and it sort of sets up the binding between those two. So it says, before this point, I just created this file descriptor, and I said, oh, it's going to speak IPv4, but I didn't say who it was going to talk to, and what was it connected to, okay? On my end, what is it connected to on my end? This does that association, right? You associate the server socket address with the socket descriptor. Okay. Okay. So that. And again, if you use these get address info, then you can get the arguments you need for this call in a protocol generic way. All right, so now we've got this, we've gotten this, and now we've got this mapping. We know that this file descriptor is associated with this server's socket address. And now the next thing the server calls is something called listen. And so this is interesting because basically the client and the server up at this point are fairly, in terms of how their file descriptors were declared, are symmetric. So there's no notion of who's initiating the call to who and so forth. So the listen is the one that sort of turns it into something that's listening as opposed to active. Okay, so that's what this says here. By default, the kernel assumes that the descriptor from a socket function is active. It will be on the client side of a connection. But the listen overrides that and says, no, this is actually going to be on the server side. So it converts it from an active socket to what's called a listening socket that can now accept requests from clients. Okay, and there is, as with some of the other things, there's an added parameter. This is a hint about the number of outstanding connection requests the kernel should queue up before starting to refuse requests. Okay, so if your server can only handle 1,000 connections at once before it just just falls on the floor, then you set that to 1,000. So now we have this file descriptor and it's actually actively listening. Okay. So the next thing that needs to happen is that the server does this accept. Okay, and that you give it the listen file descriptor. Again, the socket address and the address link. And what that tells it is that the server is now in a position to wait for connection requests from the clients. Okay, so this is a sort of, it sets it sort of, the server says, okay, I'm ready. I'm all set up to now accept requests, and then basically nothing happens. It sits there passively listening until it actually gets a request. Okay, and that occurs when the client acts and does this connect. Okay, so the connect is again another call. It takes the client file descriptor and the server side thing. I'm trying to connect to this server. Okay, and it attempts to establish a connection with that server. And if it's successful, you don't get an error flag, then you know you're good to go. Okay, and that connection is characterized, as we saw on Tuesday's lecture, by both the IP address and the port, colon the port. Okay, and on the server side, of course, that address and port are of the service. On the client side, it's still the port that that matches the service port, the one you want to talk to on the server side. But the port number is one of these ephemeral port numbers, just assigned on the client, and it's given a unique one so that you have a unique mapping between a client process and a particular client host. And again, it's best to use this get address info to make sure it's protocol independent. So here's an illustration. The server calls accept and then blocks, waiting for some client to show up. All right. The client calls connect, and that makes this request. And when it's successful, the server returns another file descriptor that's specific to this client and this connection. And now the connection is established. So you can read and write on these two file descriptors, and you will get the information packets from one side to the other. Any questions on that? Okay. So why do we have both this two types of things, sort of a connected descriptor and a listening descriptor, right? So we had, right, there's two things here. We have this descriptor here and this descriptor here. All right, well, the answer is that, there's just one of these guys, and it's sort of sitting there with its job is to field the incoming requests as they go along, where you can have any number of these guys, and their job has nothing to do with fielding new requests. It has to do with servicing connections you've already established. All right, so this is created once and exists for the lifetime of the server. This one is on a per connection basis and exists only as long as it takes to service that client. Okay, and this also allows the server to fork threads and for child processes to handle different requests. Okay, which is kind of a heavyweight way to do it. If you have lots and lots of clients, you're not going to want to fork a process for each one of them. But if you have only a few clients, then that's a way to go. Okay, so after having done all that, then we have our client file descriptor and some sort of connected file descriptor, and they're both connected and ready to do all this intermediate stuff here. Okay, and then when eventually this gets closed, it's just this guy that gets closed, right? Not the listening guy is still operated, and any other client file descriptors are still operating until that client closes it. Okay, questions on that? Yes?
When you say the server blocks it receives a request, is it like the same sort of logic we use for shell? Is it the same sort of logic we use for shell apps, like the same blocking and everything?
Yeah, it's similar. Good. All right. Okay, so that's at the high level what's going on. Now let's look at the client and look at what it actually looks like in code. Okay. So again, all this code is available to you for your use in the usual place. So this is the code for open a client file descriptor. So again, it covers, this as shown here, it covers this whole range. All right. So we can see that the first thing it does, I mentioned there's these hints. It just zeroes them all out, and then does set up some of the things, right? So we're interested in a sock stream using a particular port, and using a numerical port argument, and this is another hint flag that's useful, recommended for connections to say it's address config. So given those hints, then you feed it the host name and the port, which are the arguments to this function, and you get back this pointer to that linked list of things that match. Okay, you get a picture that looks like that. Okay, so now, as it says here, the client walks this list and tries to proceed from there. So this is walking the list, right? You start at the head of the list you're given, and you're going to walk to the next until you find something that works. So first thing you do is you try to create a socket descriptor. So you do the socket call, again, based on the family requested, the socket type, the protocol. If you get an error, then you do a continue, and that you go on to the next item in this list, right? If you get an error and you call socket, you go on to that one. Otherwise, the second step is you try to connect. So again, you give it the file descriptor and the address and the length. And if you're successful, then you've done both steps, and so you're good to go. And so you break it completely out of the loop. Okay. If you fail on this step, then you close that file descriptor and you try again. Okay, and the next one on the list. All right. And then there's some cleanup. You free the list. If all the connections happen to fail, you return an error code. Otherwise, you return the one that succeeded, which would be client FD. Okay. Questions on that? All right, let's look at the code on the server side. This is the code for open listen file descriptor. All right. So again, we start off by zeroing out all the hints, and then we set up some of the flags, accept the connection on any IP address using the port number, and then you do this call to address info to get back one of those linked lists. And again, this is referring to you now, right? So your own service. And so what you want to do there is you want to again create a socket descriptor, and we're going to store it in this listen file descriptor, as we said before. If you fail, then you go to the next one in the list. Otherwise, there's sort of for technical reasons, not that important. This is useful because it eliminates address already in use error from bind. But getting back to the main storyline, then you try bind, and if you're successful, then you're good to go. Otherwise, you close that file descriptor and try again. Okay. So at the end of that, you'll need to do some cleanup. Okay, you free the address, and again, if nothing was found, you return an error code. Otherwise, okay, so thus far we've just done socket and bind, right? So we've done this and this. We still have to do listen. So that we saved to the end here. We said we found something, so let's call listen. Okay, and if that fails, if the call to listen fails, then we close it and return an error. Otherwise, we return the file descriptor that's successfully all good to go. Okay, And both these codes are independent of any particular version of IP, which is one of the reasons that we provided them, we recommend you use them. Because when you write your proxy lab, you're gonna, there's potentially you'll be talking to both kinds of IPv4 and IPv6. Okay, so any questions on that? All right. So we're going to use Telnet to demonstrate some things. So Telnet, you give it a host and a port number, and it creates a connection with for that host and port number. Okay. So let's see. So Echo Server I, that was the server side of our code for the Echo Server that we went through in detail. Last time we saw a little bit of the code. Here we just highlighted at high level what it does. Now, this is going to serve as our client. So this is our client. And so we do a telnet into the server. Okay. And so you will see, trying to connect. This is the IP address, as you can see here, actually. It's the IP address for Whaleshark. Okay. So it tries it, connects it, and so forth. Then you get back here that you indeed are connected, and you get this client, this ephemeral port. And then the client, we're echoing, so you type hi there. It gets those 11 bytes and echoes them back. Hi there, howdy, 8 bytes and howdy. Okay, exit, you quit, connection gets closed, and you're good to go. Okay. All right, so that's kind of what it looks like at the terminal. Any questions on that? All right, so now that you know at that level, now let's up level and talk about web servers, okay, and HTTP. So you're probably very familiar with a lot of this, okay, right? You've got your client browser, you've got some web server, you make HTTP requests, and you get back the content in HTTP response. Okay. The current version is HTTP /1.1. That's been in place for a while now. Okay. And you can read all about it, which I'm sure is pretty boring reading at this URL here. Okay. So this is, remembering when we talked about IP, IP talks about datagrams being delivered. TCP sort of assembles those into entire streams where you preserve, you ensure reliability, ensure order, and the web content will go on top of the TCP protocol. Okay, so what is content? It's a sequence of bytes and associated what's called a MIME type. Okay, you've probably seen some of these, like HTML has a MIME type of text/HTML. Your image might have a type of image /JPEG and so forth. Okay, and equally good bedtime reading. You get a complete list of MIME types at that URL. All right, if that doesn't put you to sleep, I don't know what will. Okay, so you're probably familiar with the notion of static versus dynamic content. Static content is already pre-stored in a file, in files, and just retrieved. Okay, so that might be certain images or audio clips, HTML files, and so forth. More interesting, and again, you'll be dealing with this in your proxy lab, is dynamic content, and that's content produced on the fly. Okay, so it's, for instance, content produced by a program executed by the server on behalf of the client, and the requested files are actually executable code, right? So it's going to run some code. And maybe that code, I don't know, deciding what ad to display for you or whatever, right? But there's some dynamic thing that every time you go to the page, it might be different. You might look at, some cookies it's got stored away and decide what to show you on the page based on, I don't know, what's in your shopping cart or whatever. But it'll be done dynamically. It's not sort of the same thing every time you go there. Okay? And all that content is managed by the server. Any questions on that? Okay, probably all familiar with URLs. Okay, you may be aware that the prefix of the URL is used by the client to know sort of where the server is, what the port is, and what the protocol is. Okay, and the server, once it gets there, picks up on the path from there. Okay, so the path from there makes sense for on the server side. Okay, and one thing that could be slightly confusing is that although this is a path name, it doesn't start from the root of like a file system. The default is it starts from the home directory for the requested content. So index.html will be a file sitting in the home directory that you land on based on that URL and that port and IP address when it comes to the server and the IP address and the port. So it's okay just to have a slash, which defaults to typically index.html. Okay, you've probably seen that maybe when you set up your own web pages and so forth. So there can be a little bit of challenge to determine if the request is static or dynamic, because there's no hard and fast rules for this. But one nice convention is if you have a CGI bin directory and you put all the dynamic content in there. And that's basically what we're going to do to simplify the discussion in this class and in your labs, is that we'll distinguish dynamic content by having it be in CGI bin directory. So we'll look for that in the path. Questions on that? Okay, good. HTTP requests. The most thing you're probably used to is the GET request. That's the one that says, I'm a client, I want to fetch something. There's also, a POST, which is, you sort of push the information the other way, and some ones that are less common. Okay, so it takes a method, which is like GET or POST. It takes a URI, which is either the URL for a proxy of the URL suffix for servers, and a version like HTTP 1.1. Okay, and then there's a bunch of request headers that are a series of header name, header data, provide additional information to the server. Okay, and we'll go through an example in more detail in a little bit. Any questions on that so far? Okay. So response is a response line followed by 0 or more response headers, possibly followed by content. And it's important to note that there's a blank line that separates the headers from the content. Okay. So here's what a response line looks like. There's a version, a status code, a status map. Hopefully, if everything goes well, you get a status code of 200, and that means everything's okay. But you may be familiar from browsing of getting a 404, right, which is a not found. There's also, I think it's 401, it's permission denied and so forth. Some of the other ones you may have seen a lot. The headers, so typical kind of header is like a content type header, which will give one of these MIME things, right, like text/HTML and a content length. Okay, questions on that? All right, so here's an example in this gory detail. So the first thing is the client opens a connection to the server using, in this case, Telnet, and you see it all gets connected. And then the client makes a request. So it's a GET request, and it's going to use this protocol. And the host is cmu.edu. And the empty line terminates the headers. Okay? And then the server response you get back is actually an error message. You get back that, okay, this is the protocol, here's the tag, and here's what it means. 301, okay, moved permanently. And then you get various headers indicating the date and the server. And because it's moved permanently, it actually tells you the location of where the page is moved. Okay? So what this is saying is that this defaulted, as I mentioned, to index.html, whereas the headers, the page is actually index.shtml. Okay, so that's why it failed, but it told you where to look next. Okay, but here's the headers, and an empty line terminates the headers, and then you can have a bunch of content. You've got the HTML tags, so this is the HTML content, and eventually closes the connection. Okay, so that was a failure, so we try again. And this time, the GET request, we actually take the new location, the corrected location, and it comes back okay. Everything works. Okay? Any questions on that? Okay, good. All right, we'll see if you really had no questions. You know, I went so fast, it's not open yet. Hold on. All right, can you get it now? All right, let's see how people did. All right. So the connect function, all right, most people got this right. It's called by the client to establish a connection with the server. So this was the other way around. The server doesn't do the connect, the client does the connect. What is the function that's called by the server to wait for connection?
Listen.
That's listen. And what's called by the server to, called by a server to wait for a connection is accept, right? You can read to wait for a connect call. What about this one? What's called by a server to associate a socket address with a socket descriptor?
Bind.
That's bind. Good. Good. All right. What separates a header from content? It's always a blank line. It doesn't matter whether it's static or dynamic content. All right, good. Let you off easy. Only 2 questions this time. Any questions on the quiz? So now we're going to spend most of the rest of the lecture talking about the tiny web server that you're going to, that has sort of rudimentary functionality of a web server, and you can look at the code and help you learn structure things and learn how things work. It's very little, very tiny, right? Only 239 lines, and so of course it's not as complete or robust as a real server. There's all sorts of ways you can break it. It's really kind of just a toy, but it will illustrate the main code paths through a web server, and it will serve both static and dynamic content to real browsers. Okay, so what can it do? It can accept a connection from a client. It can read a request from a client via the connected socket. It can split into method. Remember I said there were 3 fields: method, URI, and version. But it's only set up to handle GET requests, GET methods. So if it's not a GET, it'll return an error, whereas a real web browser would be able to handle all the different method calls that put and so forth. If the URI contains this text string in it, then it's assumed it's dynamic content. So of course it's easy to mess it up, right? Because it's just doing a text string. So the fact that CGI bin is part of this URL will definitely confuse it. And it will do the heavyweight thing of forking a process to execute the program. Otherwise, it just serves the static content. All right, so let's look at that first, serving the static content. All right, so you have, there's a file descriptor and a file name and a file size. And, okay, so the server has to create all the headers and response and stuff. So the first thing it does is it calls this routine called getFileType, which will take the file name and basically just look at the extension of it, right? If it's .html, it will know it's an HTML file and so forth. And it will get you the file type that you can use and store it in there. And then, so now it starts to print into this buffer what it needs to print in. So remember, the response always starts with the protocol. Okay, this is an old one. It uses 1.0, but everything was okay. So it gives you the 200 code, and every line has to be ended with \r/n. Then it says I'm going to print this header server. This is the tiny web server. Connection, close, connection length. So it gets that from the file size. Connection type, it gets it from the file type, which is computed. And then now that it's filled up that buffer, it does the Rio write to that file descriptor. Okay, and so that's kind of all the headers. And then it goes ahead and opens the file read-only, and maps, does sort of memory maps the file to the connection, and then it does a write of that, and then it unmemory maps between the two. So it's just a way of getting the contents of the file quickly into conveniently into this buffer. Okay. All right. I was about to say it forgot to have the blank line between the headers and the content, but you can see it's right here actually. All right. This is the RN that finishes off this previous thing, and here's your blank line. Okay, so that's how you get that blank line that separates the header from the content. All right, so for dynamic content, so for instance, something where the path might be this, CGI bin n.pl. Okay, so it's dynamic content. The server creates a child process using fork, and runs the program identified by URL in the process. That NPL gets run inside that process. So when it gets run, there's some content that gets generated, and the server captures that content. We'll show you in a minute how it does that. And then after it's done that, then it's eventually going to send it back to the client. Okay, so some of the issues in serving dynamic content. So this program may have arguments. Okay, how do you get the arguments to that program? How does the client pass arguments to the server? Anybody know the answer to that one? By just looking at your own URLs sometimes? Yes.
It's like the question mark. And
Exactly.
Something equals.
Yeah, yeah. Question mark, and then you can have a chain of arguments and values. How does the server pass these arguments to the child? How does the server pass other information relevant to the request of the child? How does it capture this content coming back? Right? I mean, it's not coming back, it's just being produced by this program. You may have an idea on how it does that, actually. What's the mechanism by which we can redirect? So this program here is likely going to either spit to its contents to a file, or more likely even to stand it out. So what command have you seen that we could use to make sure that instead gets someplace the server can see it? What? I think that's it. Duke 2. Yeah, okay. That's that one. Okay, and there's a whole CGI, Common Gateway Interface specification that deals with this. Okay, often called CGI programs. Okay, so CGI is the original standard. That's the one we're going to be using in this course because it's the sort of the initial and the simplest. But there's all sorts of other faster techniques that people have used. And as I mentioned, creating a process on the fly is a very heavyweight thing to do, right? So much better off to do something, say in a Java VM or something, so you don't have to fork off an entire process just to get, say the protections you want. All right. Okay, so we've created a website. It's the most useful website you'll ever see. It's called add.com. You give it 2 numbers, and it adds them for you. Okay? No problem. I'm sure the IPO of the startup is just around the corner. I'm sure we'll get billions. Okay. So you can already see some of what's going on, right? We've got a CGI bin. Right, so the port happened to be assigned 15213. The CGI bin, so that means this is a program. The program is called adder, and its 2 arguments are 15213 and 18213. Okay. So host, port, CGI program arguments. And what you get back. Okay. So as we mentioned, the arguments are appended with with a question mark. Arguments are separated by ampersand. Because you can't have spaces, you often see this %20 that replaces the spaces in what you can say arguments you type into a form or whatever that gets submitted. And okay, we already said that. So how do you get from the server to the client? So it turns out there's an environment variable called query string, and the server will put the arguments into basically set that environment variable to be equal to that. So so within adder, okay, so adder needs to get the arguments. So how does it get the arguments? It goes to this query string and parses it basically, right? So you go and you find where the ampersand is. You know that there's only 2 arguments in this. So you find the single ampersand, and you null terminate there, so that kills that finishes off that string. and then you copy the rest as well. Okay. So that's how you get these, and then you convert them to number integers, and that's how you get the two numbers to add, and then it will magically add them, of course, and spit out the answer. All right, so this is now the question about how does the server capture the content produced by the child, and we use our friend Duke2. Okay, so this is again serving dynamic content. So first you generate the response. Okay, everything was okay. Again, you're using a really old HTTP protocol, and so you spit that out. Then you start with your headers, and you spit that out. And then you do this fork, and you set the query string to be these the arguments, okay, that you've teased out before. And then you set up your Duke2 to redirect standard out to the file descriptor that got passed in, and only then do you do the fork, and you run the program. With these things set up, and then you wait. You wait until the child is null, and then read. Okay, questions on that? All right, good. All right, here's the response body. Welcome to ad.com, the Internet Edition portal. And then, of course, the answer is this N1 you got back plus the N2 you get back, and then the sum. Okay, and then you say thanks for visiting, and then you put in the content length, which you're able to calculate, and the content type, and then the actual content, and then you flush it. Okay, so what's important to notice here is that it's actually the child process that knows the content type and length, so it must generate all those headers. You can't, unlike you can't just generate the header and then call the child. The child has to have within it the ability to generate its own headers, because for things like the length, for instance, that's not even determined often until the CGI program actually runs, and you see how big it ended up being. Questions on that? Okay, so how does it look? What shows up as you're running? So again, we do this telnet, and we get connected. Then here's our get to our adder in that protocol. Okay, connection close. Connected length was 117, and it was in HTML, and generated by the CGI program. You get the answer is, thanks for visiting, connection closed by foreign host, and you're done. Okay, so that's what you see at your terminal, but we know now all the code that gets executed in order to produce that. Right. All right, so for more information, there's Richard Stevens wrote a whole series of books that are very, very helpful. This one is a good resource for network programming. And as mentioned, there's complete versions of all the code in this lecture. If you go to the schedule link and you see, PowerPoint and PDF, and soon there'll be video, you'll also see code. And you click on code, and this lecture will last. You get to the directory where all the code is, including the tiny server. And you can use any of this code in your assignments. Okay, you'll find it helpful as you're getting started on the Proxy Lab to have access to that code. Okay. All right. You know, I was so worried about not finishing on time because I had to catch up from the last section. That I probably went through that way too fast. But we got done 20 minutes early. So enjoy. 20 more minutes to work on your Maryland class. All right, good.